Good morning, dear students. In yesterday's class, we have discussed the Poisson's ratio. Okay, and in today's class, we are discussing the elastic potential energy stored in a stretched wire. Okay, so elastic potential energy is being stored in a stretched wire, or prove that potential energy per unit volume of stretched wire under force is equal to half stress into strain. So this we have to prove here. Okay. So they may ask in the exam, okay, obtain an expression for potential energy stored in a stretched wire. Prove that potential energy per unit volume of a stretched wire under force, which is equal to half into stress into strain. Okay, so that is what we have to do here. Now let us consider a wire, okay, which is being fixed to a rigid support. We are considering a wire of length L. Okay. Now this wire is being stretched by a force. By applying a force, we are stretching this wire. Okay. Now what happens when we stretch this wire? When we stretch this wire, then there will be increase in the length of the wire. So then the total length of the wire will be L plus small l. So here L is the increase in length here. Capital L is the original length here. Say for example here the length of the wire is 15 centimeter. Now it is here the force is being applied here. Due to this force, okay, a strain is being produced. So due to that, there will be change in the dimension of this wire. So the dimension is how it is changing. The length is changing here. Okay. So 15 centimeter. After stretching, it will be increased to 15.5 centimeter. That 0.5 centimeter will be our increase in length, and 15 centimeter will be our original length here. So this is how when we are applying some force. Okay, when we apply some force on this wire, so when we are stretching this wire, there will be increase in the length, so that L is the increase in length of the wire. Okay, so now we know that here there is a tensile stress. There is a tensile stress is being acting here. Tensile stress where force is acting per unit area. Okay, where the length is increasing. Okay, now and also a strain is being produced. What type of strain? That is longitudinal strain. There is change in length to the original length here. So that is what change in length is how much? L here. So we know that Haines modulus of elasticity definition. Haines modulus of elasticity definition. So we know Haines modulus can be written as a stress by strain. Stress by strain here. Right. So now stress means tensile stress is being activated. Strain means longitudinal strain is being produced. Okay. When tensile stress is being applied on this wire, then the longitudinal strain is going to be produced in the wire. So this stress can be written as, that is, F by A. As we know the definition, stress F by A. Strain means change in length to the original length. Now what is the change in length here? L. L by capital L. So I can write this as F into L divided by A into L. So this will be our Haines modulus of elasticity. Okay. So Now how much force is being applied here? So to calculate that one, we will rearrange this relation. F equal to y into a into L divided by small l. So this is the cross multiplication, y into a into L divided by L. So this will give a force which is being applied on this wire. Now when we are applying some force means, see, whenever we are applying some force on any body, then there will be change in the position of that body. Then we can say that the work is done. Right? The work is done. Suppose let us say for example there is a stone is kept on a table. A wooden block is kept on a table. When I am applying some force on that wooden block, then it changes its position. So when it changes its position, that means we can say that the work is done. So the same thing, when we are applying some force on this wire, there will be some change in the length here. So change in length is happening means the work is done. So a small amount of work is being done here. So that small amount of work will be dW is equal to force into small change in the length. That is dl means what? Small change in the length. So force into displacement we can say. As we know from the definition, what is work done? Work done is always equal to force into displacement. Here I am writing work done means force into displacement. Displacement. So this is the force here it is acting. This is our force. Displacement means what? Length here. So let us say that length is small change in length because I am doing small work done here. Okay. For small work done, there will be small change in the length, that is force. Okay. Now, if I substitute here, now dW is equal to force means how much? Y A. Let us substitute here. Force means Y into A into L divided by L into dl. So this is our small work done. But here the change in length is how much? L here. It is not dl here. Okay. So therefore total work done you have to calculate here. So the total work done in stretching a wire with the increase of length L. So let us integrate with 0 to L here. So to calculate that one, so integrating on both sides here. Integrating on both sides. So on both sides with limit 0 to L, because we are doing some work from 0 to L here. Okay, 0 से L तक हम work length change हो रहा है. So इसके आप क्या करें? Total work done is equal to 0 to L. That is Y A L divided by L into dl. Okay. Now, so integration means what is the total work done is? I can write this as W is equal to, as these are all the constant terms here. Okay. So I can write Y A into L, integration of 0 to L, 1 by L into dl. Okay. So we are integrating from 0 to L here. Okay. There is 1 by L into dl. Right. So now W is equal to. So let us integrate from 0 to L here. So dear students, there is some small correction here. So L goes to the numerator here. That means I can write this as F into L divided by small l. Okay. So here I am writing F equal to YA into L divided by L. So I have done a small mistake here. Sorry for that. So this L goes to the numerator, just like I am writing here. F by A into L by L, like this. Okay. So Y A by L divided by L. So here it becomes L by capital L. L by capital L. So that is divided by L is L. So now if we integrate with respect to L here, then it becomes YA integration of L with respect to dl. So limit 0 to L means it is L square by 2 here. Okay. So this will be our total work done. That is W is equal to half Y A by L into it is L square. So I can also write this as W is equal to half Y A L square divided by L. Okay, so total I am writing W is equal to half Y A L square divided by L. So this is our total work done here. Okay. So whatever the work we are doing here, that is being stored as a potential energy. So the work done per unit volume will be always equal to the potential energy per unit volume. Okay. So the work done per unit volume is equal to the potential energy per unit volume. So that is being stored as a potential energy. So therefore I can write this as half Y A L square divided by L into per unit volume means 1 by volume. So therefore I can write this as half Y A L square divided by L into, that is 1 by volume means area into length of this wire. So A into L. Right. So therefore I can write this as half. Here A will get cancels. Y L square divided by L square. So therefore half Y, that is L divided by L whole square. So where I can write this as half. Y means stress by strain. So I can write this as stress by strain. And here change in length to the original. Change in length is how much? L here. Capital L means original length. So therefore I can write this as change in length means strain by L by L means this is change in length divided by original length is called as strain. So therefore I can write this as strain whole square. As we know from the definition, that is from definition, strain is equal to what? Change in length to the original length. So therefore change in length divided by original length is called as strain. So here strain, this strain will get cancelled. One strain will get cancelled. So therefore half stress into strain. Here it remains here. One strain here it remains. So therefore half stress into strain is equal to, that is work done per unit volume. That means, so the potential energy per unit volume is equal to half stress into strain. So this is what we have derived here. Okay. So potential energy per unit volume of a stretched wire under force is always equal to stress into strain. Okay. So this is what we have derived. So here just I have done a small mistake here. That is F into L divided by A into L. So F into L divided by A into L. So integrating on both sides. So we got there is half stress into strain. Okay. So this is what the derivation for the elastic potential which is stored in the stretched wire. Okay. So in the next class we will discuss the numericals based on this chapter. If we have any doubts based on this derivation, you can ask the doubts through the comments, or especially, and we have made a group also. On that group also you can ask the doubts based on this derivation. Okay. Thank you, dear students.